Hello everyone, my name is Samir Deshmukh. I am a first year doctoral student at Rio Yokota lab at the Tokyo Institute of Technology in Japan. Today, I will be talking about our poster on distributed memory task based block low rank direct solver. As you all know, the death of Moore's law has led to a new era of parallel hardware. Specialized hardware with highly parallel processing units like GPUs and TPUs are becoming increasingly common, and also the number of cores per CPU is increasing as opposed to the clock speed of single CPUs that were common during the Moore's law era. The dense LU factorization is a very useful technique for factorizing a dense matrix in numerical problems arising out of electromagnetism, statistics, and machine learning. Although very useful, it takes about O of n cube time, which is prohibitively large for most problem sizes. Moreover, new highly parallel and low precision hardware cannot take direct advantage of this technique. In order to solve some of these issues, we turn to a matrix format called the block low rank matrix format. This format reduces the time taken for computing an LU factorization from O of n cube to O of n square and preserves the accuracy of for computing an LU factorization for at up to 10 raised to minus 6 for double precision calculations. This is done by subdividing a large dense matrix into low rank and dense blocks, with the off diagonals being low rank blocks and the diagonals being dense blocks. The off diagonal blocks are represented as SVD factorizations of the corresponding dense blocks. Now, if you try to parallelize these matrices on large supercomputers, we run into several problems relating to process distribution, communication, and load balance. Basically, how do we manage all these trade offs in order to come up with an ideal solution that gives us the optimum performance for a given machine and problem size? An answer to one of these problems is to use a runtime system for optimizing the load balance of the computation. A load a runtime system expresses a computation as a bunch of tasks and dependencies in a directed acyclic graph, where the individual computation kernels of the LU factorization are tasks within the DAG, and the data dependencies between them are the edges. Parallel tasks that do not depend on each other can be executed in parallel very easily, and communication and computation can be overlapped easily. Our results for a block low rank multi-node strong scaling have been very promising. You can see on the graph on the upper left that the task-based block low rank solver, which is red, scales almost ideally uh, 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 for an execution with multiple nodes and single threads, and this is caused because because the runtime system is able to schedule the resources efficiently, thus maximizing the compute time and minimizing the wait and overhead time, which does not happen for other dense computations. However, when we run our computation on a single node with multiple threads, we find that the positive scaling continues until 25 threads, and after that starts reducing. This is because in a block low rank computation, the low rank factorizations, which are irregular and memory dominant, tend to tend to dominate the computation time, whereas this is not the case for a dense factorization. This can be seen in the bandwidth utilization graph on the bottom, where you can see that after 25 threads, the bandwidth utilization decreases. Thank you very much for your time. You can contact us at the email IDs, and thank you for sponsors and ISC20 for making this poster reality. Thank you very much.